Yeah, we must move on now. Our final speaker this morning is Michael Bycroft from the University of Cambridge. Hello. And Michael's going to be speaking about what has natural history done for physics, the case of electricity in 19th century France. Thank you, Michael.
Okay, thanks very much for attending and listening, and I hope my talk has something of interest for historians of 19th century physics, even though it is about 18th century physics rather than about 19th century physics. And my talk today is slightly different from what was presented in my abstract. In the next 15 and a half minutes, I'm going to try and answer the question at the beginning of my title, what has natural history done for physics? It's going to be a very incomplete answer. I'm focusing on one small case study from early in the 18th century, but it's going to be a positive answer in the sense that I'm going to argue that natural history did indeed do something for Charles Dufay's absorption theory of electrics, and as a bonus I'm going to argue that this particular theory, his theory of electrics, was novel in his time, that it was distinctive, almost no one else adopted this theory, and also that it has to a large extent been overlooked by historians of Dufay and of electricity. But before I turn to Dufay, let me give you some historiographical background on natural physics and natural history and experimental physics, or histoire naturelle and la physique expérimentale, as I see them in the 18th century. There are two fairly iconic images from 18th century French science. On the left, the frontispiece for l'histologie et la consciologie of a man called Joseph Antoine Desailliers d'Argenville, a French writer of best-selling popular works on especially shells and stones. Argenville was not particularly interested in explaining things, not particularly interested in carrying out experiments. He was a natural historian in the sense that he was interested in collecting, classifying, and describing objects in the three kingdoms of nature, and especially of shells and minerals. Contrast that mode of inquiry with the one epitomized on the right. This is an image drawn from a defining text in mid-18th century experimental physics, the Essai sur l'électricité des corps of Jean-Antoine Nollet, who was himself a man who helped to define experimental physics in France in the mid-18th century. Nollet certainly was interested in explaining things. The upper part of this image depicts his attempt to explain the attractions and repulsions that result when you rub a glass tube. The circle in the middle is the cross-section of the glass tube, and he was certainly interested in carrying out experiments. This is an early depiction of the famous Leiden experiment. My historiographical claim, which I won't be able to explain in any detail here, is that historians have not done enough to find especially methodological connections between these two forms of 18th century science. And in order to show that there were indeed some connections, I'm going to look at this man, Charles-François de Cisternay-Dufay. He had a short life, but he had a very active one, and the bulk of it he spent, or a large part of his working life, he spent as a chemist at the Royal Academy of Sciences, which he entered in 1723. To give a bit of context, the 1730s, which is when his career really got off the ground. This was the decade in which Hervé, the great French naturalist, was writing his influential text on insects. It was also the decade in which Pierre Maupertuis and other members of the Academy travelled to Lapland to investigate the question of the shape of the Earth. And the history of electricity, this is just after major discoveries from the English experimenters Stephen Gray and Francis Hawksbee. Gray discovered what we would call electrical conduction, what he called electrical communication, and Hawksbee carried out detailed studies of electroluminescence. Obviously this was before Benjamin Franklin came along. It was before the Leiden experiment was invented, as we saw on the previous slide, and obviously it was before anything like Volta's battery or Coulomb's law came along. Dufay is most well known for his contributions to electricity, in particular for showing that electricity was a more or less ubiquitous phenomena in nature, was present in just about every substance, for discovering new phenomena like electrical shocks and electrical sparks, and also for distinguishing most famously between what we would call positive and negative electricity and what he called resonance and vitreous electricity, and for stating two rules which are staples of undergraduate physics textbooks today, that bodies endowed with like electricities tend to repel each other, and bodies endowed with unlike electricities tend to attract each other. Now, Dufay is a good case for my topic because he had a foot in both of these camps. Obviously, he was interested in experimental physics with his work on electricity. At the same time, however, less obviously, but just as importantly, he was linked to natural history. He was acquainted with Argenville. Argenville published one of Dufay's early works. Dufay also shared Argenville's passion for precious stones. Dufay built up a large collection of precious stones which he bequeathed to the Jardin du Roi. Upon his death, the Jardin du Roi was the leading institution of natural history in Paris and possibly in Europe in this period. And non-trivially, Dufay was also the intendant du Jardin du Roi during the 1730s, the director of the Jardin du Roi. Let me now turn to his absorption theory of electrics. So what I'm calling his absorption theory of electrics is not his term, the phrase, this is mine. Insisted in his answers to 4 questions, 2 of which are on this slide and 2 of which will be on the next slide. I claim that, as I mentioned at the beginning, that this theory was novel. The questions that he was asking, he was the first to give systematically pose these questions and give answers to them. But perhaps more interestingly, his answers were, in many respects, unique to him. So, question 1, how should the distinction be drawn between electrics and non-electrics? Dufay's answer was that electrics are those bodies which are easy to excite. That is, if you rub them and then you hold light objects in their vicinity, like gold leaf or bits of chaff or bits of paper, then those bodies will be attracted and repelled. In this class were things like glass and amber. Non-electrics are those bodies that are hard to excite. That is, either they can't be excited by rubbing, or they have to be eaten in advance in order to be excited. In this category, things like wood, paper, and metals. Today's terminology is a bit confusing for us because his electrics roughly correspond to our non-conductors, whereas his non-electrics roughly correspond to our conductors. We'll see in a moment why it's important not to use those terms conductor and non-conductor when talking about Dufay. Question 2, what are the rules of electrics? That is to say, how do non-electrics and electrics differ in their electrical behavior? Dufay's answer to this question consisted in a series of rules, of which I have given 8. Non-electrics are bad supporters, we would say bad insulators, but good transmitters, we would say good conductors. Also, they are good attractees, detractors, interceptors, light throwers, and spark deliverers. I won't go through each of these phenomena in detail. The important point is that all but one of these rules were original to Dufay. So the first of these, non-electrics are bad supporters, was implicit in the work of Stephen Gray, but all the other ones had not been stated prior to Dufay, and as far as I can tell, had not been suspected prior to Dufay. Here's where it gets more interesting, perhaps. This is where the distinctiveness of his theory comes out. Question 3, which of the rules of electrics explains the others? In other words, which of these rules that I listed on the previous page, which of these is more fundamental than the others? Dufay's answer was that the rule that non-electrics are the best contractors was more fundamental than all the others. By contraction, he meant the tendency of certain bodies to acquire an electric virtue when approached by a rubbed glass tube. That's what he meant by contraction. And the rule that he stated here, that things like metals are better contractors than things like amber and glass, is what he called the contraction law. Note the contrast between this answer and the answer that we might give, and also the answer that his student Nollet gave later on. We tend to think of what he called transmission and what we call conduction as more fundamental than the other properties which I listed on the previous page. For example, we would say that the rule of induction, or water transmission, helps to explain the rule of supports, because we know that metals are good conductors. This means that they're very ineffective as supports for things we want to electrify, because they drain the electrical matter. They provide no barrier between the electrical matter, the excited object, and the ground. That's not Dufay's take on something like supports. He thinks contraction is more fundamental than induction. To help make sense of his explanations, it's useful to consider his answer to the fourth question: how do non-electrics interact with electrical matter? His answer was to think of electrical matter as a kind of fluid which easily enters non-electrics, like metals, easily moves through them. That might not be surprising, but the last bit in italics is the surprising bit, but has trouble getting out. He didn't express things like this. Instead, he used the term absorption to describe the action of non-electrics, and I suspect that he had in his mind the sponge image, an image which was attributed to him by Mallet. He thought of things like metals as sponges which absorbed electrical matter and held on to them once they were imbibed. That may be contrasted with our view, or at least with Mallet's view. Mallet tended to compare metals not to a sponge, but to pipes, or canals, or rivers. In this case, electrical matter enters them easily, moves easily through them, and also moves easily out the other end. Now that might seem a trivial difference, but it made a difference when it came to explaining the rules of electrics. Thank you. Not only did these two theories, or images, give different explanations for some of these phenomena, sometimes they made contrasting predictions, and on some occasions the sponge theory gave better predictions than the pipe theory or the canal theory. For example, consider the rule that Dufay observed that non-electrics are good interceptors. By this he meant that things like metals, represented by the grey rectangle there, tend to block the action of a rubbed glass tube. That is to say that light objects on the other side of the barrier tend not to be agitated when the tube is held there. Dufay could explain this by saying that the metals soak up or absorb the electrical matter from the tube. Mallet couldn't explain this. His theory gave the opposite result. For him, metals are highly permeable bodies which transmit the electrical matter, and for him, glass rather than their metals should be the best interceptors. What does all this have to do with natural history? I'll talk about this very quickly. One thing to note is the resemblance between Dufay's rules of electrics and the kind of rules you find in works by naturalists who are interested in classifying different materials. Take Dufay's rule of interception: non-electrics intercept electricity, whereas electrics do not. Compare that to a rule that Réaumur, his patron, stated a couple of years before Dufay's papers on electricity came out. Earths expand when wet, whereas sands do not. I call these taxonomic laws. What they have in common is that they both express a contrast between the properties of two classes of material. They may be contrasted with something which I would not call a taxonomical law. Dufay's law that excited bodies are repelled by excited bodies, whereas unexcited bodies are attracted by excited bodies. So this law or rule also expresses a contrast between two kinds of objects, but those two kinds of objects don't correspond to two classes of materials. They correspond to two states of objects: excitement and non-excitement. But there wasn't just a resemblance between Dufay's rules and natural history. There was also a genetic connection, which can be seen if you go back to the passage in which he first stated the distinction between electrics and non-electrics, this distinction which underlaid his rules of electrics. I won't read this through in detail. I'll just mention that the materials for which Dufay first observed the distinction were those in his cabinet of precious stones, like agates and jaspers, porphyry, granite, and marbles. Also that he saw this distinction as a classification of stones. Finally, that one of the properties here, hardness, plays a double role here. In the first sentence, or first section here, Hardness plays a role of a mineralogical character, which it was at the time. It was used by Argenville, for example, to distinguish different species of stone. Down here, though, it's used as a physical variable which helps to consolidate the phase distinction by electrics and non-electrics. And it does this because Dufay finds a correlation between the hardness of stones and the ease with which they are electrified. Wider implications. This is my last slide. This is not the only place in which Dufay made use of his mineral collection in his work on electricity and in his other work on experimental physics. He also used that collection to make inductions, to achieve experimental control, and also as components in precision instruments. A broader point is that this angle on Dufay's research helps us better appreciate the role of René Hayama, his patron in the history of experimental physics. He tends to be, to some extent, marginalized in the history of experimental physics and seen as a naturalist rather than a physicist. However, he certainly played a central role in Dufay's career, and Dufay borrowed from him probably some precious stones, since Hayama had his own collection at the time, and he may also have borrowed this fundamental role from his patron, since Hayama deployed this metaphor in his work on steel making, on porcelain, and in his efforts to classify stones and earths, all of which he was doing in the 1720s and 1730s. Thirdly, the distinctiveness of Dufay's theory of electrics has a flip side, which is the originality of Nollé's theory of electrics. Nollé didn't just continue or propagate Dufay's theory, but radically revised it to produce something more like the present-day theory. Two final points is that by looking at theories of electrics, we can better appreciate the vitality of French alluvial theories in the 1740s and 50s. And finally, really broadly, Dufay was the first in a long line of what I call physicist naturalists at the Jardin du Roi, the institution that later became the Muséum National d'Histoire Naturelle. Georges Buffon and Auguste Hoey, and in the 19th century, people like Antoine César Becquerel and Edmond Becquerel, and for 19th century historians of physics, Henri Becquerel. Thank you.
Thank you very much indeed. Does anybody have a question for Michael?
I wonder if there is another kind of natural history in this period which as well played a role in electrical thinking. And I'm thinking of meteorological and astronomical phenomena. More specifically, we have a series in the same period concerning the aurora borealis, and especially the theory of Méran in France. These people also try to explain the aurora in terms of electrical effluvia and things like that, a tradition which goes back to Halley.
Yes, and you're absolutely right. Dufay himself wrote a paper on paraheli, and also in his paper on magnetism, he linked the phenomenon of the aurora borealis to magnetic phenomena, and he explained magnetic phenomena in terms of the motions of something like the electrical matter. So yes, that's another link to natural history. I suppose natural history has lots of different strands in this period. The strand I wanted to focus on is the one that comes out of Argenville's work, which involves collecting lots of objects and putting them in a cabinet, and then classifying them and describing them.
Thank you very much. Well,